Imagine this. Every year, the world produces over 100,000 tons of titanium, a metal that has become a true symbol of innovation and strength in aviation, space, and energy. It's from this metal that the story of creating ultralight and super strong alloys begins, used for manufacturing the most critical parts of airplanes, rockets, and even geothermal equipment. In America, where titanium production technologies have reached the highest level, this metal has become indispensable in creating the future, combining lightness with extraordinary strength. Next, I'll tell you how titanium is born, from raw material to a high-tech material that is changing the world. The history of titanium production begins at the end of the 18th century, when in 1791, a British clergyman and amateur mineralogist, William Gregor, discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, pure metal was first successfully obtained only in 1825 by the Swedish chemist Berzelius, although at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and a real breakthrough occurred in 1925 when Dutch scientists Van Arkel and de Boer developed a method for obtaining high-purity titanium, which opened the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the United States, where the metal became indispensable in aviation, the space industry, and the military industry. The production of titanium begins with the extraction of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in the form of placer or primary deposits and are widely distributed throughout the world, particularly in Australia, Canada, China, Norway, and South Africa. After extraction, the ore undergoes complex multi-stage processing. First, it is enriched, separating the titanium minerals from the gangue, obtaining ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, titanium tetrachloride is reduced with magnesium or sodium in special reactors at a high temperature in an inert atmosphere, producing spongy titanium, a porous metal powder. This spongy titanium is then subjected to pressing, melting, and casting to obtain ingots or blanks for further processing. The production of titanium is energy-intensive and expensive due to the complexity of technological processes and the need to work in high-purity conditions. The main industrial method for obtaining titanium is the Kroll process, which remains the standard in the world. It includes chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, which makes it possible to obtain high-quality metal for aviation, space technology, medicine, and other industries. Thus, the production of titanium begins with the extraction of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex multi-stage technological process that begins with the extraction and preparation of titanium-bearing raw materials, primarily ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. For this, concentrates of titanium ores are subjected to chlorination in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and gaseous chlorine react with the raw material, forming titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation, obtaining high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at a high temperature. As a result, spongy titanium is formed, a porous metal powder that contains impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the spongy titanium is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used for the production of alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is spongy titanium. It looks nothing like a regular metal bar, but rather like a piece of metal sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First of all, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that improve its properties. To obtain an alloy, alloying elements are added to molten titanium, most often aluminum, vanadium, molybdenum, iron, or niobium. These impurities change the metal's structure, increase its strength, heat resistance, corrosion resistance, and improve its processability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, and after that, it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more plastic, and passed through special rolls. Rolling allows for reducing the thickness of the metal, giving it the required shape and size, as well as improving its structure and mechanical properties. As a result, various types of rolled products are obtained: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. Sheet metal is made from rolled products, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are characterized by high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and titanium alloys are used. These can be mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometry that are impossible to produce using traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are needed. In addition, to improve the performance characteristics, titanium products can be subjected to heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used to make up 15% of the weight of a modern passenger aircraft, which significantly reduces its overall weight and increases fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability. Every hour, over 20 million tons of bolts and nuts are produced worldwide. These small parts hold together skyscrapers, highways, airplanes, and even bridges between continents. But what if I told you that behind this everyday reality lies a whole world, with acids, dyes, temperatures of 1,200 degrees Fahrenheit, and robots that stamp out 300 bolts per minute? In the finale, you will see how the imperfect ones are rejected, and where they disappear to. Watch until the end, because something awaits you that isn't shown in any official report. A factory for the mass production of bolts and nuts is a high-tech enterprise where metal is transformed into indispensable fasteners used in construction, mechanical engineering, automotive manufacturing, and many other industries. The production of bolts and nuts is a complex, multi-stage process that combines mechanical processing, stamping, heat treatment, quality control, and packaging. The first stage is raw material preparation. High-quality steel wire rod, or bar stock, is used for making bolts and nuts, which undergoes cleaning from rust and contaminants. The most common method is chemical cleaning, specifically pickling in acid solutions, for example, in sulfuric or hydrochloric acid. This process dissolves scale and rust, leaving the metal surface clean and ready for further processing. After acid pickling, the blanks are thoroughly rinsed in fresh water to remove acid residues and then dried. For additional cleaning and removal of mechanical contaminants, sandblasting or mechanical grinding is used. Sometimes electrochemical cleaning is also used, which simultaneously evens out the surface and improves corrosion resistance. In large-scale productions, combined cleaning lines are often used, where the metal passes through several stages: mechanical removal of contaminants, chemical pickling, rinsing, and drying. To control the quality of cleaning, visual inspection and special devices that determine the level of surface cleanliness are used. After this, the metal is coated with a protective layer that prevents corrosion during storage and processing. The main technologies for making bolts are cold heading and turning. Cold heading is a process in which metal blanks are formed under high pressure without heating. The blank passes through a sequence of press dies that give it the shape of a bolt. First, a round base is formed. Then a head is gradually created, most often hexagonal, which allows the bolt to be tightened with a wrench. Stamping allows for producing bolts with high precision and strength, and also reduces material waste. After forming the head and body of the bolt, the next stage is thread cutting. The thread is applied by the cold rolling method, where the blank passes between special rollers that form the thread, turns without removing metal. This method ensures high thread strength and product durability. In production, speeds of up to 300 bolts per minute can be achieved. For the production of nuts, hot forging is used. Steel blanks are heated to a temperature of 1,200 degrees Celsius to make the metal plastic, and then under a press, the hexagonal shape of the nut is formed. After this, a hole is punched in the nuts, and an internal thread is cut on special thread cutting machines. Nuts also undergo heat treatment to increase strength and wear resistance. Heat treatment is an important production stage, including quenching and tempering. Quenching consists of rapidly cooling heated products, which makes the steel hard but brittle. Tempering is the subsequent heating to a moderate temperature, which reduces brittleness while maintaining strength. These processes provide the required strength class for bolts and nuts. After heat treatment, bolts and nuts undergo thorough quality control. Samples are checked for compliance with dimensions, strength, thread accuracy, and appearance. Micrometers, calipers, and special devices for checking threads are used for measurement. Products that do not meet the standards are rejected or sent for rework. To protect against corrosion, bolts and nuts are often coated with anti-corrosion layers, zinc plating, painting, or the application of special coatings. This extends the service life of the products, especially in harsh climatic conditions. Finished bolts and nuts are sorted by size and strength class, packaged in industrial containers, and prepared for shipment. Modern factories are equipped with automated lines that ensure high productivity, hundreds of thousands of products per day. First, the products are transported along conveyors to automatic sorting machines, which use optical sensors and calipers to determine the size and quality of each bolt or nut. Non-compliant or damaged parts are rejected and sent for rework or disposal. This stage ensures that only products that meet the standards go to the packaging line. Next, the bolts and nuts go to dispensers that accurately measure the required number of products for each package. These can be small plastic bags, cardboard boxes, or special containers, depending on the customer's requirements and the product's purpose. The packaging is often labeled with information about the size, strength class, manufacturer, and production date. In some cases, especially for large orders, packaging is done in industrial bags or large containers that facilitate transportation and storage. It is important that the entire process is controlled by automatic systems that ensure the packaging is airtight and protects the products from moisture, dust, and mechanical damage. Although most operations are automated, at some stages, especially when forming special kits or non-standard orders, manual labor may be used. Workers control the quality of packaging, assemble sets of bolts and nuts, place them in boxes, and prepare them for shipment. This approach allows for taking into account individual customer wishes and ensuring maximum accuracy. After packaging, the finished products undergo a final control stage, checking the labeling and integrity of the packaging. Then the products are sorted in the warehouse by orders and prepared for shipment. In addition to standard bolts and nuts, many enterprises manufacture non-standard products according to individual customer drawings. This allows for meeting the needs of specialized industries, for example, aviation, mechanical engineering, or construction. The global market for fasteners, including bolts and nuts, is showing stable growth, driven by several key factors. First, the development of construction, the growth of infrastructure projects, the construction of residential complexes, bridges, roads, and commercial facilities stimulates the demand for metal fasteners. Investments in infrastructure modernization in many countries, especially in Asia, Europe, and North America, directly affect the increase in the production of bolts and nuts, as they are the basis of reliable structures. Second, the growth of mechanical engineering and automotive manufacturing supports the demand for high-quality fasteners. The automotive industry is actively implementing new technologies and materials, which requires precise and strong bolts and nuts to ensure the safety and durability of vehicles. In particular, in Europe, an increase in car production of more than 2% is expected in 2025, which stimulates the demand for metal products, including fasteners. Another important factor is the technological modernization of the metallurgical industry, which allows for the production of higher quality and specialized products. The introduction of digital technologies, automation, and new processing methods increases the competitiveness of manufacturers and expands opportunities to meet the growing needs of the market. Draw the right conclusions that this is a profitable business. The cost of raw materials, particularly iron ore and energy carriers, also affects production volumes. Price fluctuations can stimulate or restrain production, but overall demand for metal products remains high due to the needs of key economic sectors. Every hour worldwide, there are dozens of nuclear reactions, but only a few know that at the heart of every atomic bomb is a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, created by human hands. You will learn how ordinary uranium gives birth to an explosion with the force of thousands of suns, why the sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret is hidden inside a nuclear warhead? Watch until the end, because the finale will change your perception of the modern world. In ancient times, when the world was just learning to hear the voice of the atom, a few curious minds peered into the invisible, into the heart of matter. Those were the years when science was fumbling in the dark, but with great aspiration. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered uranium can be split. It was like ice cracking on a river, under which a giant was sleeping. While Europe was preparing for war, a group of people, later to be called the Lords of the Atomic Flame, secretly gathered across the ocean. The Manhattan Project began in the New Mexico desert. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, under the dawn clouds, the first nuclear bomb exploded. The sand turned to glass, the sky to fire. And amidst the complete silence, one scientist whispered, "Now I am become death, the destroyer of worlds." But the story didn't end there. A few days later, Hiroshima and Nagasaki became pages of sorrow. And when the world thought it had seen everything, the USSR responded. Under the leadership of Igor Kurchatov, the first Soviet atomic bomb exploded in 1949, and a decade later, the Tsar Bomba. Its power could destroy a city the size of Paris. The irony of history is that nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. The ideas of security, control, and diplomacy became more important than combat. For the first time, humanity posed global questions. Can we agree to survive together? Thus, the doctrine of deterrence emerged. Do not attack, because you know that an attack will turn into a catastrophe. And although this balance can hardly be called ideal, it provided decades without a global war between superpowers. An entire era, cold, anxious, but without massive fronts. Nuclear research gave birth to new fields: nuclear energy, reactors on submarines, medical diagnostics. Even space projects received a boost thanks to the understanding of the atom. To create the most terrible, we learned to comprehend the most complex. Yes, nuclear weapons are a danger, but they are also a mirror of human wisdom. We created something super powerful and did not use it on a massive scale. This is a story about a force that we decided to restrain. About a science that taught us not to dominate, but to coexist. In the depths of laboratories, where the light of lamps dimly illuminates blueprints, the journey to creating a nuclear bomb begins. This is not just an assembly of metal. It is the alchemy of modernity, where every gram of substance has the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction. But uranium in nature is mostly uranium-238, which is not suitable, so it is enriched. The 235 isotope is separated using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It is obtained in nuclear reactors, where uranium absorbs neutrons and turns into the plutonium needed for a nuclear bomb. The external appearance of a nuclear bomb often resembles a classic aerial bomb. A streamlined metal body designed for stable descent from a great height. In a huge hangar, where the walls ring with the echo of metal, the air smells of hot steel and lubricant. Here begins the birth of the shell that must contain the heart of the atomic explosion. From the red-hot maw of an industrial furnace comes a stream of metal, a special steel reinforced with nickel, chromium, and manganese. Its temperature is over 1,000 degrees Fahrenheit. The summer sun pales in comparison to this fire. Masters, in protective suits with transparent shields, watch the forming. On presses with a force of hundreds of tons, a steel sheet is bent into a streamlined shape. Before their eyes, an elongated body is born, resembling a drop of water, frozen under the pressure of the heavens. Next, mechanical arms mill internal partitions. Cut holes for tail stabilizers and locks. Every millimeter is the result of careful calculation, because the balance during the fall depends on it. After this, the body undergoes a strengthening ritual. Immersion in an anti-corrosion bath, treatment with a polymer coating, and a matte paint finish. The color is dark green, similar to a military shadow on a slope of pines. And finally, testing. It is dropped from a height, struck with hammers, rotated in a wind tunnel. quiet laboratory, semi-darkness, a light smell of ozone. Something heavy hangs in the air. Before you lies an open nuclear bomb, its metal walls removed, and its insides, like an organism, lie exposed. There is nothing superfluous here. No shine, no decorations. Only function, only explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear charge. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in the palm of your hand. Its shape is mathematical perfection, polished to the micron. Around this sphere is a whole symphony of pressure. Composite explosives, layer by layer, resemble a flower, folded inside out. Their task is not just to explode, but to make the explosion happen inside. Like palms squeezing to the limit, these explosive lenses must create an implosion, a uniform, ruthless compression that will make the substance supercritical. If even 1 second is delayed, the entire structure will become a meaningless pile of metal. And in the very heart of this implosion orchestra, the initiator. A small device waiting for the moment to release the first neutrons. Polonium and beryllium interact, creating a tiny storm capable of starting the irreversible. It is from this that the chain reaction will begin. A match to an atomic forest. Then, a layer of tamper. Heavy as a shadow, it envelops the heart of the bomb, not to protect, but to contain. Uranium-238 or tungsten are not active, but extremely important. Their task is to delay the neutrons, to make them return, like an echo in a cave. The duration of the explosion, its power, its apex, all depend on this. In the tail of the body, the brain. Automation, electronics, wires and sensors. Barometers await altitude. Radars watch the ground. Batteries slumber, ready to awaken. Here it is decided when everything must happen. Over a city, in the air, after the fall. Without this nervous system, the explosion would be an accident. But here it is, a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, the sections of an encyclopedia of power. The outer casing, smooth and cold, the layer of explosives, mathematically arranged, the tamper, an invisible guardian, the core, like the seed of the future, and in the very center, a spark that sleeps until it is awakened. In 62 years, 2,065 nuclear explosions have occurred in the world. 5,224 is not the number of nuclear explosions, but an approximate estimate of the total US arsenal, including active, reserve, and dismantled warheads. But the number of nuclear tests that the US conducted from 1945 to 1992 is 1,154 explosions, and each of them is a separate page in the history of power, fear, and science. The first explosion, Trinity, on July 16, 1945, in the New Mexico desert. This was the beginning of an era when the energy of the atom became a weapon. It was followed by Hiroshima and Nagasaki, the only instances of the combat use of nuclear weapons. In the following decades, the US tested bombs on the atolls of Eniwetok and Bikini, in Nevada, underground, in the atmosphere, and over water. The explosions had different purposes. Testing new designs, demonstrating power, studying the effects on technology and living organisms. The power varied, from a few kilotons to 15 megatons, as in the Castle Bravo test of 1954. In 1952, the US conducted the first thermonuclear test, Ivy Mike. This was no longer just a bomb, but a miniature star created by man. The explosion destroyed an entire island. In the 1960s, testing became regular. The US tested warheads for missiles, aerial bombs, and even neutron charges, which had a minimal blast wave but maximum radiation. The last official explosion took place on September 23, 1992, after which the US declared a moratorium. But the arsenal remained. It is being modernized, adapted, and maintained. Some warheads are on submarines, some on strategic bombers, and some in NATO storage facilities. These explosions are not just technical events. They are a story of how humanity learned to control the energy of the stars and put it at the service of fear. Every year, over 50,000 tons of neodymium magnets are produced worldwide. Without them, electric cars, smartphones, and even rockets wouldn't work. But few people know that it all begins with dirty ore, mined at depths of hundreds of feet. To turn it into a super powerful magnet, it must go through more than 10 complex stages, where every second and every degree matters. There's a moment where the material explodes from within. Why? If you watch until the end, you'll discover a technological secret that even the world's largest manufacturers keep hidden. The mining and primary processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundation for obtaining the necessary components is laid. This process begins with the large-scale mining of ore containing rare earth elements, which are part of neodymium. In the first stage, the ore is extracted from the Earth's crust using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of deposit. After extraction, large pieces of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size to smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed to mills, where further fine grinding takes place to a powder or pulp state, consisting of fine ore particles suspended in water. The next critically important stage is ore beneficiation, the goal of which is to separate the rare earth minerals from the gangue. This process can include various methods. One of the most common methods is froth flotation, where the crushed ore is mixed with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a foam that is then collected. Heavier particles settle faster, allowing them to be separated from lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After beneficiation, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not pure metal. It requires further chemical processing, which usually includes dissolving valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the individual separation of each rare earth element and its purification to a high degree. For example, neodymium is separated from other rare earth elements such as praseodymium or samarium. The final result of this complex chain of processes is obtaining high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary for obtaining the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most important stages in the production of high-performance neodymium magnets: alloying. This process requires extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy that provides unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for example, to increase the magnet's thermal stability, improve resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret of many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important, as it prevents the oxidation of rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would worsen the material's magnetic properties. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving complete melting and homogenization of the alloy, the stage of rapid cooling begins, known as the strip casting method. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating cooled drum. Contact with the cold surface of the drum leads to extremely rapid cooling of the melt at a rate of up to millions of degrees per second. Such extremely rapid cooling prevents the formation of large crystalline grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material has the form of thin flakes or ribbons that are easily crumbled. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be fixed in the subsequent stages of production. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron-boron alloy have been formed, the stage called hydrogen decrepitation begins. This is an innovative and highly effective method used for the primary crushing of the obtained material before further fine milling. The essence of the process lies in the interaction of hydrogen with certain components of the alloy, particularly with neodymium. Neodymium, being a rare earth metal, has a high chemical affinity for hydrogen and is capable of forming hydrides. When the alloy flakes or ribbons are placed in a controlled environment where they are exposed to gaseous hydrogen, the hydrogen begins to penetrate the material's structure. The penetration of hydrogen atoms into the crystal lattice of neodymium and the formation of hydrides leads to a significant expansion of the volume of the crystalline grains. This expansion creates enormous internal stress within the material. Since the alloy is already relatively brittle, these internal stresses lead to the formation of numerous microcracks along the grain boundaries and within them. As a result, the material becomes extremely brittle and literally breaks down into small particles that are much smaller than the original flakes. This process occurs without the use of mechanical grinding, which avoids significant contamination of the material from mill elements and reduces energy costs. In addition, hydrogen decrepitation occurs mainly along the grain boundaries, which ensures the preservation of the magnetic properties of individual grains that were already formed during the rapid cooling stage. The powder obtained after hydrogen decrepitation is an intermediate link in the production of neodymium magnets. It is not yet fine enough for pressing and sintering, but it already has a much smaller size, which makes the next stage, jet milling, more economically viable and technologically manageable. This stage demonstrates how the chemical properties of elements are used to optimize physical processes in metallurgy. The powder is pressed into a solid block in a vacuum under a strong magnetic field. This field orients the grains so that their magnetic domains are aligned in the desired direction. The block is immersed in a cold, isostatic press under high pressure to remove residual air gaps. The pressed block is placed in a furnace at a very high temperature, over 2,000 degrees Fahrenheit, just below the metal's melting point. This process allows the blocks to achieve full density and develop their magnetic and mechanical properties. After sintering, the blocks are reheat treated at lower temperatures to relieve internal stresses. The resulting magnets are cut and ground to the desired shape. Due to the high cost of the material, waste is minimized. Most neodymium magnets are coated with a protective layer, usually nickel-copper-nickel, to prevent corrosion. At this stage, the magnets have a preferred direction of magnetization, but are not yet magnetized. They are placed in a fixture that briefly exposes the magnet to a very strong magnetic field. After the field is removed, the magnetic field remains in the magnet. Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines. Burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core. A steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even 1/4 of an inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro-roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied. Marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this: in every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense, solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle. inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added. And it's ready for transportation and installation.